Swayam Prabha. Digital India. Educated India.
So, what we will do is, see, as we go into the this subject, we will need keep needing concepts from some or the other branches of mathematics. So, I will introduce some of these concepts in the beginning. Okay. We will also tell you what it means for a solution to exist and when is there a solution and so on. So, you have to, thankfully, there are some blanket theorems that we can apply, which guarantee the existence of a solution. So, you have to make sure that the problem you have at hand satisfies the assumptions of those theorems, and then you have existence for free, no problem. You do not have to. So, the existence question can become a chicken and egg problem, because the existence should not require you to claiming the existence should not require you to actually compute what you are hoping exists, right. So, you should have a way of claiming existence that does not require finding the solution in the first place. Okay. So, thankfully, there are such results. So, we will go through those. So, we'll start with this. So, first simple idea we need is that of a. So, I will start with just a review of real analysis and later also some convexity. Okay. So, the first concept we need is that of a sequence. Okay. And in this course, we will stick to problems that are in Euclidean spaces. So, in Rn, okay. A lot of what I will teach you can also be applied in larger spaces, okay. But we will mostly stick to Rn. So, I will talk of a sequence here, which is in Rn. So, the way we will write this is, so you have a point x that lies in Rn. Now, you have, and a sequence is just a series of such points. Okay. So, this is x. So, here is a point x1, here is another point x2, etc., etc. Okay, x3, etc. So, a sequence is denoted like this, x sub k, with, and on outside the bracket you write k in it. So, you have, so a sequence is an infinite series of points x1, x2, x3, etc., etc., all lying in a common space. So, all of them, say, suppose belong to Rn. Now, since we are in Rn, we can talk of how far is this sequence. There is a certain, sequences have a certain direction in which they go, right. As k increases, you can sort of think of them as a moving particle or whatever, or a fly that is flying around in this room. So, at time 1, at time 2, at time 3, etc., where is this particle currently? This is how you can track a sequence. And so, since we are in Rn, we can, so here is the origin of your space, and we can talk of how far where is this sequence headed, right. So, as first, we say that the sequence is bounded. We say it is bounded if you have the following. So, if you look at this particular figure, this sequence is traveling all over the place. The indices keep going on and on till infinity. The sequence keeps traveling. we say it is bounded if there is some big ball centered at the origin, if there is a ball centered at the origin in which the entire sequence resides. Okay. We say Xn is bounded if there exists an m, let us say greater than 0, such that if I take the norm of xk, norm of xk is nothing but the distance of xk from the origin, norm of xk is less than equal to m for all k in natural numbers. So, we say it is bounded if it's if the sequence, if the norm of x of every point in the sequence is no more than m. There is a so notice the sequence, the order in which this is being stated. We want a common m that will work for all k. We want there exists an m such that for all k norm of xk is less than equal to m. All right. You can of course find an m that is tailored to a particular to each point. So, then that does not make the sequence itself bounded. That just means that every point has a finite, would have a finite norm. All right. So, here we are asking for a common m such that the norm of xk is less than equal to m for all k. So, the picture you should have in mind is that there is this ball of radius m here, in which this entire sequence is lying. Of course, the ball is not necessarily minimal or in any sense, it is just some ball of finite radius. Okay. It is not minimal in any sense, means that it does not mean that you cannot find a smaller ball or anything like that. But all that matters is that the entire sequence is within the ball. Okay. In that case, we say it is bounded. Now, I said that we can follow the sequence along its progression as k increases, and you can ask, okay, where is this sequence headed? So, simple answer is, firstly, is it at least not running away eventually? So, is it not running away? For example, if you have a sequence xk, say for example in R, let us take a sequence in R, say xk equal to k square, right. Such a sequence, what would happen to such a sequence? This is a sequence that keeps increasing as k increases. Eventually, if you look at it along the real line, here is your 0 of the real line, at k equal to 1 it is at 1, at k equal to 2 it is gone to 4, at k equal to 3 it is gone to 9, and so on, so forth. Eventually, it will just it keeps blowing up, it increases and increases. There is no m that you can specify such that all the elements of the sequence are within m, right, within have absolute value less than m. Okay. So, this sort of sequence is not bounded. Let us take another example. Consider the sequence xk equal to minus 1 to the k, minus 1 raised to k. How does this sequence behave? It oscillates between plus 1 and minus 1, right. So, at k equal to 1, it is at k equal to 1, it is at minus 1, at k equal to 2, it is at 1, k equal to 3, it goes back to minus 1, 4 at 1, etc., etc. Is this sequence bounded? Right. It is bounded. It is bounded because I can put all the elements of that sequence can all be enclosed within this plus minus 2 region, right. So, I can take, say for example, m equal to 2, then the absolute value of xk, or the norm which is the absolute value of xk, would be less than equal to n. So, this sequence is bounded. Now, just because it is bounded does not mean the sequence is headed somewhere. Sequence could still dance around all the time without having any particular direction. But interesting sequences are those are those, and which we are always interested in, are these sequences that may initially dance around for a long time, but eventually head somewhere, right. What this is saying is, so we say that xk converges to x star if the following is true. You tell me, you specify a distance, you specify what it means to be close to x star, and well, you specify it by saying, okay, well, I want it to be within the distance between x and x star to be no more than epsilon. You specify the epsilon. Okay. So, for every epsilon that you specify, now it is for me a challenge. I have to now tell you, is the sequence going to be within epsilon of x star? Unfortunately, usually it is not the case that the entire sequence is going to be within epsilon of x star, but then maybe not the full sequence, but does the sequence eventually end up within epsilon of x star, within epsilon distance of x star? What does it mean for it eventually to end up? So, for every epsilon that you throw as a challenge to me, I should be able to produce an n naught. I should be able to produce an n naught such that from the point n naught onwards, the sequence completely lies within an epsilon distance of x star. So, from n naught onwards, I am within this. So, the picture you should have in mind is, so again let us draw a pair of axes. Here is your origin, here is the sequence. Initially it can do whatever it wants, maybe, and but eventually it has this behavior where it seems to be tending towards some point, and that is it. I can't even draw this more finely. Here somewhere here is the x star. It's headed here, and then eventually after a point, all the elements of the sequence are accumulating around x star, and eventually, since for every epsilon I should be able to find this find an n naught like this, it means that however small you make the epsilon, infinitely many of points of the sequence are actually within epsilon of x star, within epsilon distance of x star. Only the first n naught are going to be outside, right. And however small I make the epsilon, means I can make the epsilon 10 raised to minus 10, and still within that are going to be infinitely many points, and outside only finitely many. I can make it 10 raised to minus 20, still within that are going to be infinitely many, and outside are going to be only finitely many. Okay. So, from a certain, there will be a point onwards from which it is going to be inside them, right. So, let us take an example. Let us take xk equal to 1 by k. Okay. Again, a sequence of real numbers, xk equal to 1 by k. What does this converge, and if it converges to what? Converges to 0. Why does it converge to 0? As k increases, it becomes smaller and smaller. That is while that is true, we need to say it based on this definition, based on the definition that I have stated. So for every epsilon greater than 0, can you find for me an n naught? Can you find for me an n naught such that for beyond n naught, all the xk's for k greater than n naught have absolute value less than epsilon. Yeah, precisely. So what I can do is, what I need is that this I need to find an n naught. So you're giving me an epsilon, which is positive, and I need to find an n naught. What will I take my n naught as? What I can do is I can take n naught as I can do this, right. So I can take n naught as 1 by epsilon and just seal that to the greatest integer, the smallest integer greater than 1 by epsilon. Okay. Then what would happen from, so x n naught itself is going to be definitely less than x n naught is going to be definitely less than equal to 1 by epsilon, or I can make this plus 1. So, this is definitely less than 1 by epsilon. X n naught is less than 1 by epsilon, and not only x n naught plus 1, x n naught plus 2, etc. all of them are, so not 1 by epsilon, sorry, epsilon, sorry, my mistake. X n naught is going to be less than epsilon, and not only that, x n naught plus 1, x n naught plus 2, x n naught plus 3, all of them are going to be less than 1 by epsilon, right. So, in short, the sequence, as you can see, is going to it may have a large number of values that are away from 0, but infinitely many. From a certain point onwards, all of them are going to be as close to 0 as you like, right. So, x star in this case is called the limit of the sequence. It is called the limit of this sequence xk. Okay. And it is very easy to show that limit of a sequence, if it exists, is unique. You cannot have a sequence that converges to two different points. I did not specify this, and it is not, it is generally, it is not needed, because we are talking of distances between points, between xk and x star. No, but then they have to be, if you have a point in a different space, then you need to embed all of them in the same space. So a distance like this is meaningful, provided both distance between 2 points is meaningful, provided they both have the same number of coordinates at least. So both must have n coordinates in this case. Okay, so we talked of, so what it means to converge. So limit of a sequence, if it exists, is unique. Now, can you tell me what it means for a limit to not exist? When does a sequence not have a limit? That does not say that the limit does not exist. That just says that the limit is not x star. So let's first do the simple thing. What does it mean for a sequence to not converge to a given point x star? It means that there exists, so let me write the simpler version. So the answer to this is exists greater than 0 such that for all n naught in natural numbers xk minus x star is greater than equal to epsilon for some k greater. What does this mean? So, when a sequence is not converging to it may converge, but it's certainly not converging to this particular x star that I'm considering. Okay, when a sequence is not converging to this particular x star, it means that I can find an epsilon ball around that x star, an epsilon radius region around that x star, such that no matter where you start, no matter which n naught you start from, there is always going to be at least one k after that which escapes from that region. There is going to be one xk after that n naught such that xk escapes from that. Is this clear? So, what this means is, so the way this looks is, so here's suppose my x star, and I should be able to find some epsilon region around it. Okay, so here's this epsilon radius. So and the way the sequence will behave is that sequence may come inside, but goes outside once, maybe come inside again, goes outside again, come inside again, but goes outside again, etc., etc. Point is, it never eventually lies inside. So, it keeps going out infinitely many times. So, you look at the sequence from any n naught onwards, you will always find one point from there onwards which is escaped from any n naught onwards, no matter how large your n naught is. So, you can never find an n naught such that the sequence from here onwards is forever inside. Okay. So, there is such a sized ball, okay, for which this holds. Okay. And usually this such a, so to make this true, the ball has to become would have to become very small. So, this will become easier and easier if the ball is smaller, because it will becomes easier for the sequences points to escape from it. Right. If you throw your net very wide, obviously many points will lie inside, but there exists such an epsilon that becomes easier to show once your epsilon becomes smaller. Okay. So, the sequence keeps escaping like this. Okay. Now, if you look at this, these points that have escaped, okay. So, for every n naught, I can find one xk with k greater than n naught that has escaped, right. So, let me just call that something. So, let me call that this particular k, this k, let us just index it by, let us call it k n naught, k sub n naught. Okay. So, what it means is this, there is always an xk n naught which has gone out, right. And not only that, there is such a xk n naught for every n naught, right, for every n naught. So, this itself, right, these points, this set of points itself can be thought of as a sequence, right. So, they are traveling, this is a, so this here is an example of a subsequence of xk, of the original sequence. So, a subsequence a subsequence is formed like this. You have your sequence x1, x2, x3, etc. The way you construct a subsequence is by you take a subset of the indices. So, you take kn, you consider a sequence of natural numbers like this. You consider the k1, k2, dot dot dot, these are natural numbers, such that this ki plus 1 is strictly greater than ki. Right. So, when you index the index the subscript here, the natural number jumps by a positive amount. Okay, ki plus 1 is strictly greater than. Then you can, with this, once I have this, so this is now a strictly increasing sequence of natural number. I can use these as indices on my original sequence, and that gives me a subsequence. See, if I, so this is just a subtle technical point. If I didn't have this, this point here where I am asking for strictly greater, right, the sequence could go backwards also. So, that changes the direction of motion of the sequence. So, we do not allow that in the definition of the subsequence. If you have equality, the sequence stalls. Although I is getting indexed, ki remains the same. So, essentially you are repeating the same point from the original sequence. We do not want to allow that. We want the subsequence to move alongside the sequence, okay, and in the same direction. So, k1, k2, k3 are just indices. These are natural numbers. These are just some natural numbers. So, I am going to use these to index k. To index my original sequence. I am going to look at the sequence at k1, k2, k3, etc. For example, k1 could be 2, k2 could be 7, suppose, etc. So, as I look at the sequence with these indices only, what I get is a subsequence of the entire sequence. So, we will stop here now. We will continue this in the next class.